Neutrosophic Borda method. This video is based on our paper which was published in 2022, and you can look into the bibliography at the end of this video and check this paper. It is based on the definition of so-called single-valued Neutrosophic sets. Single-valued because, as maybe you know, the most general definition of Neutrosophic sets presented by Smarandache is connected with the whole concept of non-standard analysis and non-standard subsets of 0-1 closed interval. But the most typical and the most practical approach is the one which is called single-valued. So assume that we have some non-empty universe X, capital X, and then a single-valued Neutrosophic set A on X can be defined as follows. Our A is a collection of, as you can see, of quadruples of the form X, small x, so it's for each element of our universe, and each element gets its degree of being in A, degree of indeterminacy, IA, and degree of falsity of not being in our set A. We assume that T, I, and F are some numbers from the interval 0, 1, and that they sum up to something between 0 and 3, including 0 and 3. So as you can see, and as maybe you know, the whole idea is a generalization of fuzzy sets invented by Zadeh and intuitionistic fuzzy sets invented by Atanasov. Now assume that we have m options, alternatives, objects, m scenarios, as some would say, and they are rated on n criteria, so parameters, because we have multi-criteria decision problem, and we'll solve it using Neutrosophic Borda method, Neutrosophic variant of Borda method, of Borda count. So scenarios are x1 to xm, and criteria are e1, e2, and finally en. Some of these criteria are beneficial, so we prefer bigger values are better, and some are cost. It means that lower values, like lower price, are better. So the whole structure may be presented in this tabular form. Scenario x2 and criterion 2, for example, gives us x22. Criterion n gives us x2n. Scenario m, criterion n gives us xmn, and so on. For any I and for any j, as you can see, xij is this triple. These are Neutrosophic evaluations of our object with respect to criterion j. On the next pages, we shall show all the basic steps of our algorithm in its simplest form. So, for example, without weights, without weighting system. So, for each criterion, so for each column, as you can see here, for each criterion ej, where j belongs from 1 to n, we have that. If it is a benefit criterion, then we arrange the values of truth evaluations for our object I in descending order, while the values of indeterminacy and falsity are in ascending order. This is because finally we would like to have the best values on the first place, then on the second place, and so on. So we assume that if our criterion is a benefit one, then we are deeply satisfied when the values of truth are high. Yes, so it means that we have, you know, a big high probability that yes, our object is good with respect to this criterion. Contrary to this, we prefer low values of falsity, and moreover we prefer low values of indeterminacy because it's not good to have something indeterminate that we are not sure if it is good or not. If our criterion is a cost criterion, then again indeterminacy is in ascending order from the lowest values, which are the worst, to which are the best, to the biggest values, which are the worst. But in case of falsity, we have descending order. So if something has good falsity value, then it's okay, because this is a cost criterion. So if we say that something is expensive and falsity of this statement is big, then it's good, and then there is a big chance that in fact it's not expensive. Contrary to this, the values of truth are in ascending order if it is a cost criterion. So of course in our paper you can read longer discussion of this issue, of this logic behind this, but I think that it's in general it's convincing. For any criterion, the rank of our object I, of xi, in the first order, so in the order of truths, for example, the rank of our object in the order of truths will be named Borda truth subrank of xij and denoted in the following manner. The rank of our object in the second order, the order of indeterminacies, will be named Borda ignorance subrank. And then we have the rank of our object in the third order, Borda falsity subrank, and denoted using this symbol. Okay. And then the next step is that for each scenario xi and for each criterion, we calculate Borda rank. So what's the Borda rank of our scenario with respect to our to the particular criterion j? We should sum up those Borda sub ranks. And then for each scenario, we sum up complements of all these Borda ranks with respect to 3m to obtain the final Borda number. To 3m, because in general we have 3 times m possible numbers of points, possible places, we could say, yes? M for truth, M for indeterminacy, and M for falsity. This is slightly more complicated. We will see this on the next page, however. And then we organize obtained Borda numbers in descending order, and the biggest numbers refer to the best scenarios. Here is some numerical example. Assume that there are 4 houses, x1, x2, x3, x4, and there are 3 parameters: beauty, which is benefit criterion, good technical condition, again benefit criterion, good truth values are okay, and high energy consumption, this is the third criterion, and here we assume that this is a cost criterion, so it's good if its falsity values are high, while its truth values should be low. We prefer low. And assume that we have the following Neutrosophic evaluations in this table. Scenario criterion, yes, as you can see. So for example, object number 4, house number 4 has 0.20 our estimation of truth of the statement that it's beautiful, 0.30 of our level of indeterminacy, and 0.50 that it's false, that it's beautiful. Okay, and then we take the first criterion, benefit criterion of beauty, and we have the following arrangements here. You may analyze them. For example, in case of truth, from the biggest numbers, 0.80, this is scenario number 3. Then we have 0.70, scenario number 1, and they are equal x2 and x4 with 0.20. So this is a problem here, and it should be solved, in fact, but because in fact it would be better to give these 2 scenarios, number 2 and number 4, to give them something like place number 3.5, or to modify slightly this formula here. So I can admit that it's some kind of imperfectness of this algorithm in its basic form. Because as you can see, here we have only 3 possible places, not 4 possible places, because 2 scenarios have the same degree of truth with respect to this criterion, 0.20. Then we calculate ordering for indeterminacies and for falsities. and we have the following Borda ranks, which are calculated here. Moreover, in our original paper, there is a numerical mistake here. In this place, we wrote that 3 plus 4 plus 3 gives us 11. But here I corrected this, and in fact it's 10, of course. Just like here, 3 plus 3 plus 4. Then we calculate Borda ranks for other criteria. We omit all these particular calculations here, but you may find them in detailed form in our paper. And we obtain these Borda ranks. So for example, scenario number 3 and criterion 3, we have fourth place in truth ordering, the third place in indeterminacy ordering, and the fourth place in falsity ordering, and we get 3 plus 4 plus 4, it's 11 in this case. And finally, we calculate Borda numbers. This is written here according to our formula. And just as I said, there is a problem with this formula because we had the same place occupied by two objects in criterion 1 and truth value. Yes, so this should be fixed. But using this method without any changes, we obtain the following results and the following ordering, that the best scenario is x3 because we have 16 points, so it's very far from the worst place, we could say. Then x1 and x4 have 15 marks, so they are not comparable. And the worst one is x2, which has 11 marks. In general, we have x3 is better than, and here is a mistake. It should be just x1 equal to x4. Okay, and this is strictly better than x2, which has only 11 marks. Its Borda number is 11. In this paper, as you can see, we presented a system of weights and some other calculations, and we plan to expand this method to investigate interval valued Neutrosophic sets and in the nearest future. Thank you very much for your attention. Goodbye.